So we were looking at determinants, and we basically did a few very nice properties of determinants. That suppose a determinant is basically vector v1, v2, v3, let's say, where v1, v2, v3 are vectors in other column vectors. Then this determinant will basically be equal to, let's say, determinant of v1, v2 minus v3, and basically in the middle you can have anything of the format v1 plus alpha v2 plus beta v. Okay, whatever you have in the middle column can be any linear combination of v2 and v3 added to v1. The determinant remains the same. And if you, let's say, exchange any two columns, basically columns 1 and 2 have been exchanged, then this would be negative of what it was earlier. So these are some nice properties to know. So that eases up a lot of things. And the same thing happens if you have, let's say, determinant for R1, R2, R2. Suppose these are rows, row 1, row 2, row 3. So this would be negative of row 2, row 1, row 3. And this could be equal to basically row 1, row 2 plus alpha row 1 plus beta row 3, and row 2. Okay, so such things, if you do, the determinant value remains unchanged. So in light of these properties, I gave you a few. Okay, one more thing. So if any of the row goes alpha times, so alpha times row 1, row 2, row 3 will basically be alpha times determinant of row 1, row 2. And similarly, when you're looking at column vectors, then alpha times v1, v2, v3 will be equal to alpha times v1, v2. Okay, so any of the row or column goes alpha times, right? If any of the row or column goes alpha time, then the determinant goes alpha times. Then I give you these examples. So determinant B and determinant. So what's the relationship between determinant B and determinant A? What's the relationship between these two?
It's 3 times A.
I can't hear you. Can you repeat?
3 times A.
I see
It is 3 times A.
3 times A. Okay. No, that's not correct. Any other answers?
So 27 times.
Very good. 27 times A. Because I can take a 3 common from the row 1, from row 2, and 1 from row 3. So I get 3 times 3. So that's 27 times A. Okay. All right. Now this A, what's going to be the relationship here?
60.
Yeah. So determinant B. So I take 3 out here. I take 4 out here. And then I take 5 out here. Times determinant of A. So 3 into 4 into 5. So that's equal to 60 times determinant of A. Okay. All right. So let me give you an example. Suppose A is a 2 cross 2 matrix. Okay. And B is equal to twice of A. 2 times matrix A. So what's going to be determinant of B? Determinant B equals to, let's say, some kappa times of determinant A. So what's this kappa value?
So 4.
Very good, 4. Right. So this is a 2 cross 2 matrix. So A looks something like this. So A would be something like dot, 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 dot. Okay. So 2 times A, which is basically equal to B, would basically look like 2 dot, 2 times something, 2 times something, 2 times something, 2 times. So when you twice a matrix, every element goes 2 times. Okay, when you twice a matrix, every element goes 2 times. If you alpha times the matrix, then every element goes alpha times. But now what I have essentially is when I take the determinant, I have a 2 out here and I have a 2 from this column. So I can take 2 times. So this kappa basically becomes equal to 2 to power 2. So that is equal to. All right. Here, A and B, what's going to be the relationship? Vinay, why don't you answer this one?
So 15 AC into 4B plus 6. Okay, no.
No, I'm asking
Yeah, this
something of
takes
this
some time.
format. Something of this format. Relationship between determinant B and determinant A.
So 150.
Okay, who gave that answer? All right, it's not 150. It's supposed to be the homework. I thought you guys would have attempted it by now. It won't help if you don't do the homework.
So 30.
30 is also not correct. So first of all, what I do is this determinant is basically going to be equal to determinant of, let's say I subtract 2 times minus 2 times of column 1. If this is my vector 1, I subtract 2 times of column 1. So this becomes 3A, 3D, 3E, 4B plus 6A minus 6A, 4E plus 6D minus 6D, 4H plus 6G minus 6G, 5C, 5F, 5I. The whole thing is you should try to convert it into the matrix A using the column operation. So now these things cancel. So what you're left with is 3 times vector 1, 4 times vector 2, and 5 times vector 3. That's essentially what's left in the determinant. Now what would be the answer?
So mod A is 60 times mod B.
Yeah, 60 times of mod A. Sorry, mod B. Don't call it mod. That's wrong. It's determinant.
Okay.
Okay. It's determinant. And symbols are same, but it's determinant. You should know, like, depending on the topic, when am I talking about mod? When is the examiner or anybody's talking about mod, and when is he talking about determinant? Okay.
Yes.
Fine. Prove the following. If A is an n-dimensional skew symmetric or anti-symmetric matrix, that is A transpose is minus of A, then show that determinant of A is equals to 0 if n is odd. Okay, so what I have to show is that when A transpose is minus of A, then determinant of A has to be 0. Okay. So basically I have A transpose is equals to minus of A. So what's the property that we studied between determinant of A transpose and determinant of A? What was the property here? How are they related?
They will be equal.
Equal, sir.
Equal. Very good. They are equal. So they are equal. Now, if I take determinant in this case, I have determinant of A transpose must be equal to negative of determinant of A. And by this property, determinant of A transpose must be equal to determinant of A. So when I combine these two things, what I get is that determinant of A is equals to minus determinant of A, which implies that determinant of A must be equal to 0. Remember, determinant is a scalar. Determinant is not a vector or a matrix, it's a scalar. So it's a real number. So a real number is equals to the negative of itself, then the only possibility for the real number has to be 0. Right? This is clear?
Yes.
Okay. But, now, next problem. A square matrix is called nilpotent if a to the power k equals to 0 for some positive integer k. Okay, so what is a to the power k? A square is basically a multiplies by a. Okay, so if a is a n cross n matrix, sorry, if a is a n cross n matrix, then a square will also be a n cross n matrix. Right? Now, a to the power k for some whole number, for some natural number k, is going to be a multiplied by a multiplied by a k times. So what he's saying is that a to the power k is equals to 0 for some integer k. So then it's called a nilpotent. It's called a nilpotent matrix. Okay, a is not 0. A to the power k is 0. Then you have to show that for a nilpotent matrix, determinant a is equals to 0. Okay, so you have to show that for this matrix, determinant of a must be equal to 0. So how do I show that? So a to power k is equals to 0. I have to show determinant a equals to 0. So I'll take determinants on both sides. This 0 means 0, the matrix 0, by the way. This 0 is not a scalar. It's an n cross n matrix. It's a matrix of zeros. All right. A to the power k is still a matrix. Determinant a is a scalar. A to the power k is still an n cross n matrix. So when I write a to power k is equals to 0, it does not mean that it's equal to the scalar value 0. It means that it's equal to the determinant 0. The matrix of zeros, n cross n times. So here what I'll take is I'll take determinants on both sides. So determinant of a to power k, what will this value be equal to? What is determinant of a square in terms of determinant of a? Suppose determinant,
Twice of
let determinant of a equals to alpha, then a determinant of a square will be equal to what?
twice alpha.
No.
So square of mod A. Oh, sorry, determinant of A.
Yeah, square of determinant of a. Very good. Because we studied the property that determinant a into determinant b is equals to, sorry, determinant of a into b is equals to determinant a into determinant b. Right? We did this property. So what this implies is that determinant of a square is nothing but determinant of a into a. So that is equal to determinant of a into determinant of a. So that is equals to determinant of a ka whole square. Right? So determinant a square is determinant a whole square. So determinant a to power k will be equal to determinant a to the power k. I should use this. This should be equal to determinant of 0 would be. What would be the determinant of this matrix?
So 0.
0. Yeah. So determinant a is 0. So this So this basically means that determinant a, which is some alpha value. So you're basically saying that alpha to the power k must be equal to 0. So this automatically implies that alpha must be 0. There's no other way out of it. Right? Okay. A square matrix is called orthogonal if A transpose A is equals to I. Then show that the orthogonal matrix determinant A must be equal to plus minus 1. So you get the idea now what we have to do. We always take determinants on both sides. So what happens when you Take determinants on both sides of this equation.
Determinant a square on one side.
Yeah, and what will be on the other side? What is determinant of the identity matrix? I is identity matrix.
Sir, 1.
1. Very good. So a square. So if determinant A is some alpha value, then we are saying that alpha square equals to 1, which implies alpha must be equal to plus or minus 1. So that's the only logical explanation. All right. So this is the kind of questions you can expect in exam. What they'll do is they'll define some new sort of a matrix like we are doing here. Sometimes we are saying skew symmetric. Sometimes they'll say nilpotent. Sometimes they'll say orthogonal. Now these are terms you don't know. But don't even fret over it. Just because you haven't heard about it does not mean you cannot solve the question. Because here they have given you the essential property which you need to solve the question. And once you have that property, after that, what you do is important. Okay. All right. So after this, we have this proof that we have to show that this thing holds, that this determinant of this particular thing must be equal to y minus x into z minus x into z minus 1. Okay. So one thing is obviously you can use your usual cross your multiplication method. 1 times this into this, then 1 times minus 1 times this into this minus this basically, and then plus 1 times this minus this. So you can use this method. Although we are more used to going along the first row, what I'm saying is instead in this case you can go along the first column. Or if you are not very comfortable with it, you can take the transpose of this matrix 1 1 1 x y z x square y square z square. Okay, so you can take the transpose of this matrix and then you can do your usual multiplication and get answer. Okay, so that's straightforward. Another way to do this would be to convert this into triangular matrix using Gaussian elimination. Right, so if I do that, then I know that if I'm doing row operations, then my final matrix determinant value should remain the same. So let's try doing that technique because that's something new. Okay, the other technique you already know from high school, so there's nothing new there. So let's try this new technique. Determinant of 1 1 1 x y z x square y square z square. So I do this row operation, row 2 goes to row 2 minus row 1 and row 3 goes to row 3 minus row 1. So what I get is determinant of first row remains added as it is. Second row becomes 0, y minus x, y square minus x square. Third row becomes 0, z minus x, z square minus x. Right. After this, what I have to do is I have to make this term 0, pivoting on this one. So the row operation which gets this done is simply row 3 goes to row 3 minus z minus x upon y minus x times of. It's very forcible, right? I'm forcing it on it. That's what you can call it. It's very forcible, but that's how you can do it, and that will get your job done. Okay. Another thing which you can do is, you see this row. Can I take something common from this row?
Y minus x.
Very good, y minus x. So I can take y minus x common here. So what will be left here?
0 1 y plus x.
Y plus x. And similarly, you can take z minus x common here. Right. So this becomes 0, 1, z minus x. Oh, sorry, z plus x. Right? So I have my y minus x and my z minus x outside times 1x x. Okay. Now after this, the next step would be to make this thing as pivot and subtract this thing with respect to it. So what I'll do is pivot this row, make this thing 0. So the row operation will be row 3 goes to row 3 minus row 1, row 2. So I have this thing common, let me call it at k. So this becomes k times determinant of 1x x square 0 1 y plus x 0 0. This becomes y plus x, no, sorry, z plus x minus y plus x. Z plus x minus y plus x. So that basically becomes z minus y. And now, since this is a triangular matrix, what would be this determinant value? Determinant of a triangular matrix. What is determinant of a triangular matrix?
The multiplication of the diagonal.
Yeah, so what will be this
Z
matrix?
minus
Z minus y. Okay, so y minus x, z minus x, z minus y, end of proof. Okay, so these are some techniques which you will have to use maybe in exam, because right now it's a 3x3 matrix, so it's pretty easy. Okay, but if he gives you, let's say, a 10x10 matrix like this, for example, the matrix given is 1 1 1 10 times. Okay, then x y z 10 times, x square y square z square 10 times, and so on. So x cube, y cube, z cube, so on. And this goes on till x to power 9, y to power 9, z to power 9. So if this is a 10x10 matrix, then obviously I can't do it. I can't do it. So the way to do it would be to start with smaller matrices. So suppose in exam you get this exam. So how do I go about it in exam? So you start with this matrix. Let me call it as matrix A2 because it's the 2x2 matrix. My aim is to find a determinant of A10, which is the 10x10 matrix. Now what about determinant of A2? So determinant of A2 is determinant of 1x, 1y. So that would be equal to y minus x. Now determinant of A3, I have already seen 1 1 1 x y z x square y square z square will be equal to y minus x into z minus y into z minus x. Okay, so it works like this: y minus x, z minus x, z minus y. It always goes from bottom to up, y minus x. So similarly, if you have, let's say, determinant of A4, which is 1 1 1 1, let's say wxyz, w square x square y square z square, w cube x cube y cube z cube, then this determinant would be firstly x minus w, then y minus w, y minus x, and finally z minus w, z minus x, z minus y. So you can proceed in a what do you call it, inductive manner. You can inductively try doing such problems. Okay, so if you get a very complicated sort of problem like this, you can maybe use inductive logic. You can find some pattern in what's happening for A1, what's happening for A2, what's happening for A3, and then you can apply this logic for A10. Okay, so as you can see for A4, I have not even solved it. I've just given you this value. Now in exam, they can totally ask you A4. A4 is perfectly doable in exam. Now most people would go by this idea of trying to do this determinant using the normal multiplication technique. But if you start with the smaller matrices which follow the same logic and try to look for patterns, you can do it much more easily. So that would be my lesson to you, that in exam, don't always go for brute force, because if they ask you for a determinant in exam, they will try to give you a matrix which is difficult to handle with brute force, and that is easier to handle if you, let's say, have some what do you call it? Have some, yeah, if you use some shortcuts, if you use some of these properties. All right, next proof. The area of triangle in R square, this should have been R square. What typo happened here? Having vertices x1, y1, x2, y2, and x3, y3. So suppose we have a triangle which is formed using vertices x1, y1, x2, y1, and x3, y3 in R square. Okay, so some points x1, y1, x2, y2, and x3, y3. So you combine these 3 points, you get some triangle. This is asking that the area of the triangle can be calculated using this determinant. Okay, so if you use this determinant, then you can calculate the area of this triangle. So this is a tricky one, so I'll do it for you. So let's see what is this vector going to be. This vector is going to be x2 minus x3. Green color. This vector is x3 minus x2 minus x3 into y2 minus 1. And this vector, this is going to be x1 minus x3 into y1 minus 1. And when I take the determinant of these two vectors, basically the determinant of the red and the green vector, so that's going to be determinant x1 minus x3, y1 minus y3, and here, y1 minus y3, and x2 minus x3 and y2 minus y3. So this determinant is going to give me twice the area of the triangle. So let me call the area as delta. So it's going to be twice. Why is it going to be twice? Because this determinant gives me the area of this parallelopipe, which is basically twice the triangle. Okay. So the delta value should be equal to half times of this determinant. So this is my answer. Now what is this answer? This answer is basically half times of x1 minus x3 into y2 minus y3 minus y1 minus y3 into x2 minus x3. So this is my area. So I have to show that the determinant given here basically transforms into this form. That is what I want to show. Okay, so if I can show that, then my job is done. So I have to show that this value must be equal to half times of x1 minus x3 into y2 minus y3 minus y1 minus y3 into x2 minus x. Okay, so if you can show this much, then our job is done. Okay. So I want to do this in the easiest possible manner. So what I see here is that in the way I have written this, I have subtracted x3, y3 from everywhere. So what I'll do in Gaussian elimination is I'll pivot this one and I'll make these two things zero. That's how I'm doing it now. Okay, so I'm going to pivot the lowermost row. In fact, I'm going to pivot the lowermost row and I'm going to make everything above it zero. So this becomes half times of 0, x1 minus x3, y1 minus y3, 0, x2 minus x3, y2 minus y3, 0, x3, y3. Now, no, this becomes 1. Now this determinant, since these two entries are 0, you know that this determinant will be equal to basically this multiplied by this. Okay, so x1 minus x3 into y2 minus y3 minus y1 minus y3 into x2 minus x3. Everything else cancels out because these two entries are 0. Okay. So obviously this part is a bit tricky. This question is a little tricky because it requires you to equate this thing to this thing, and reaching here is a little difficult. But in exam they can ask you, because you know that a determinant is area of the parallelogram. So although I have not given you this formula that area is equal to this much, you can use the property that determinant of two vectors is the area of the parallelogram to actually generate this particular. It would classify as a difficult problem. Maybe it would come up as one of the subjective problems in ISI, but it is still in your syllabus. My bottom line here is that it's not out of syllabus. It's difficult, but it's not out of syllabus. Okay, fine. I'll leave the rest for you guys. I know you have not attempted them, so try doing them and we'll discuss them next time. Okay, these are easy ones. What is going to be this determinant value? Remember column exchanges or row exchanges when you're doing it. So that would be easier. Yeah, what would be this determinant value, guys? Come on.
Sir, 1.
Okay, so how many exchanges do I need to do? That becomes a question. So if I make this exchange, then what I get is 1 0 0 0 0 0 0 1 0 1 0 0 0 0 1 0. Okay, so this is negative. Then I'll need to, I basically want to shift this here. Okay, I want to make it an identity matrix. So then I do one more exchange. So that's going to be 1 0 0 0 0 1 0 0 0,
So
0,
minus of 1.
0, 1 and 0, 0, 1, 0. So that would be plus 1. And then I'll need one final exchange. So this would be minus times of determinant of identity matrix of size. So it's going to be minus 1. So all you needed to do is figure out how many exchanges are required, right? I mean, it's not that difficult. So you can do that. Similarly here, what's going to be the determinant value? Obviously, I know it for a triangular matrix where these entries are non-zero, but I don't know it for such a triangular matrix because the diagonal is opposed. So obviously, I want to convert into my general format and then talk about the determinant. So what's going to be the determinant of this thing? So convert it using column operations or row operations. Convert it into a usual triangular matrix, which looks like this. So convert it into this format and then we'll talk about it. Yeah. Any answers?
So 16.
16. Very good. Okay. So you do this exchange and you do this exchange. So what a couple of exchanges means no change in determinant value. So what you get is 2, 6, 2, 8. Okay. This row comes here. So 0, 2, 2, 8. This row comes in the third place. So 0, 0, 1, 4. And the final row column is going to be 0, 0, 0, 4. So now the diagonal entries are these. So the final determinant value is going to be 2 into 2 into 1 into 4. So that's 6. Third question is a little tricky. So you'll have to use a little more complicated properties, use of the properties that we have done in order to solve it. So I'll leave it to you guys. All right, fine. A lot of times lost. Luckily, determinants is not a big topic. We will be able to wrap it up. Minors and cofactors. So let A be a matrix such that this thing holds. Yeah, this is your A matrix. Then the minor Mij of this matrix is obtained by taking the determinant of the matrix obtained by removing the ith row and jth column. So Mij, suppose you want to find the minor at position 2, 3. Suppose you want to find minor at position 2, 3. So you first find the element A2, 3. You eliminate the row and column of which this particular element is a part. Okay, so you focus on this thing. You completely eliminate the column in which it is, and you eliminate the row in which it is present. And then you just look at the remaining n-1 cross n-1 elements, and then you take the determinant of those elements. So that is known as the minor of Ij. Okay, it's a complicated relationship. It's like chacha ke bua ka padosi ka Pj type ka relationship. It's a little complicated. Okay, so what is Mij? You remove ith row and jth column from the matrix and take the determinant of the remaining matrix. Okay, so M2, 3. Suppose I give you a simple matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I ask you to find minor of 1. So what you'll do is you remove the first row and the third column. Okay, and the remaining matrix you'll take the determinant 4, 5, 7, 8. So that determinant is going to be 4 8s are is 32 minus 35. So that's minus. Okay. Suppose for this same matrix, I ask you M to 1. What is this going to be? Give me the final answer. Don't give me the matrix. Just give me the final determinant answer.
-6.
Okay. So for M to 1, I would eliminate second row and first column. So what I'll be left with is determinant of 2, 3, 8, 9. So that is going to be 2 9s are 18 minus 3 8s are 24. So that is equal to -6. So that's minor of 2, 1. So that's how you find your minors. Now, minor Mij is known as the algebraic complement to the element Aij. We'll come to it in a bit. Why is it necessary? We'll look at one of the properties where minors are useful. But let's look at Laplace theorem. Laplace theorem. So generally, when we look at the determinant of a matrix, we try to find the determinant of any matrix. We always start with the first row. We always look at the first row and we proceed in the first row format. This times this cross multiplication minus this times this cross multiplication plus this times this cross multiplication. Okay. Now Laplace theorem claims that if you don't want to do it in terms of the first row or in terms of the first column, how could you do it? Okay. How could you do it if you don't want to do it in terms of the first row column? I find it very useless because frankly, you can always convert any matrix by using row of taking transposers or row exchanges. You can convert any matrix in a format where the first row is always the easiest to solve. So what I'm saying is, suppose you have to find the determinant of this particular matrix. Now, obviously, you see that the pivotal column which you should be using is this one because there are 3 zeros here anyway. Okay, if I proceed by solving it in my usual method, I'll get 1 times determinant of this matrix minus 0 times determinant of the matrix obtained by eliminating this thing. So let me call this as matrix P plus 2 times determinant of the matrix after eliminating these rows and columns. So let me call it as matrix C plus minus again minus 3 times of determinant of this matrix. Okay, so when you take any particular element, you just eliminate everything around it and you take determinant of this. Okay. Now I know that determinant, when I eliminate the row and column of which 3 is a part, it becomes the minor of what is this 1 comma 4 minor 1 comma 4 1 4. Okay, this is basically minor of 1 3. This determinant B is basically minor of 1 2, and this determinant A is basically minor of 1 1. Right? I generated this element by eliminating these two things and then taking a determinant of this matrix. So this is basically M11. So this is what we have been doing. And this is the Laplace's rule. Now Laplace did not restrict it to just being used by with respect to the first row. He gave a complete rule which is defined here, which you can start with any row or any column. But my point is, why remember this rule? Suppose you want to calculate the determinant of this matrix A. So this will be equal to the determinant of negative times the determinant of the matrix 0 0 minus 1 0 1 2 4 1 2 1 3 2 and 3 3 2 1. Okay, so you do a column exchange. It becomes easier in this format, and then you just take a transpose. If you want to work with rows, if you are more comfortable with rows, okay, fine, work with rows. 0 0 minus 1 0 1 2 4 1 2 1 3 2 3 3 2 1. Now, what is the determinant of this thing? So this becomes negative of 0 times of m1 1 minus 0 times of m1 2 plus minus 1 times m1 3 and finally plus 0 times of m1 4. Now, obviously, because of the 0, these three entries cancel out. I only need to calculate m13. How do I calculate m13? I eliminate this row and this column. The remaining matrix, you can find the determinant very easily. It's just 3 cross 3. Okay, so I'm not solving it here. The whole point is that Laplace's theorem says that you can use any row and column, but using our other properties, we already know that we can use any row or column. So even if you know Laplace's theorem or not, it's not a big deal. So that's one of the things. And to understand this, we needed to know what are the minors. So that's why I defined minors and everything. But sometimes minors are important. It's good to know what are minors of a matrix. Okay. The next is cofactor matrix. The cofactor matrix of a matrix. It's a matrix which is derived from the original matrix. So there's a matrix A. It has a cofactor matrix C. Now, when does a matrix become the cofactor matrix? So the cofactor matrix C of a matrix A is obtained by replacing each entry of A with its respective algebraic complement. Algebraic complement meaning the minors. The algebraic complement, as we have seen earlier, is calculated from the determinant of the matrix. So suppose you have this matrix. Or let's start with the matrix which, okay, no, let's do this example first, and then I'll give you another matrix to find the cofactors of. So suppose this is the original matrix A, I want to find the cofactor matrix. So the cofactor matrix will be M11, M12, M13, M21, M22, M23, M31, M32, M32. This is going to be the cofactor matrix. Now, okay, so this is going to be the cofactor matrix. Now, how do I find M11? M11, eliminate this row and column, you get this matrix, and determinant is 4. Okay. M12, you eliminate row 1, column 2, you get this matrix, but you add a negative sign in front of it because it's coming from the I plus j here is 3, which is odd. So here's the catch with finding cofactor matrices. If I plus j is odd, you'll add a negative. Okay, so this rule does not apply to finding the minors, but here it would apply. So I'll put a minus here, minus here, minus here, and minus. So wherever I plus j is odd, I'll put a negative sign. Okay. So that's how you find the cofactors of the cofactor matrix of a matrix. And simply A13, to find A13, I will look at row 1, column 3, eliminate it. I get 0, 4, 1, 0, and the determinant is minus 4. Okay. So that's how you proceed and you get this cofactor. Okay, once you have all these values, you get your cofactor.
Sir, but what is the use of finding this? Like, where can it be used?
Yeah, so that's what I'm coming to. So this Cramer's rule here. So Cramer's rule says that suppose you want to find the inverse of a matrix, you can use the transpose of cofactor matrix and divide it with determinant of A. That's Cramer's rule. Okay. I mean, obviously, we saw one technique of finding A inverse that was using Gaussian elimination. So suppose there's some 2 cross 2 matrix alpha, beta, gamma, delta, and you write 1001 here, and you use Gaussian elimination here. The aim is to convert this into identity matrix, and the same row operations you keep doing on the right hand side here, whatever you are left with will be A inverse. As soon as this gets converted into identity matrix, this will be generating the A inverse. So that's one way to get the inverse of a matrix. Cramer's rule is another way to get the inverse of a matrix. So once you find the cofactor matrix, okay, then all you need is take the transpose of this matrix. So this was my cofactor matrix C. So using this rule, C transpose will be the matrix of 24, 5, minus 4, minus 12, 3, 2, minus 2, minus 5, 4. So that's the transpose, and then you divide the entire thing by determinant of A. So you can go back to your determinant of this thing and find it, and then obviously it's a little complicated. They don't ask you questions based on this. So that's why I won't spend a lot of time on it. The kind of questions you can expect is the kind of problems that we did right before at the start of this lecture. So that is the kind of questions you can expect in an exam. These other things, they are not that important. But we never know. Maybe sometimes they ask you to find, specifically in the subjective part, they ask you to find the determinant using Cramer's rule. So in that situation, you should be able to do it. So why don't you guys try to find the determinant of this matrix, sorry, the inverse of this matrix using Cramer's rule. Okay, so I hope all of you got what Cramer's rule is. First, you find the cofactor matrix of A, C of A, and then A inverse is equals to C transpose divided by determinant. So I'll leave you guys to it. There's somebody at the door. I will just be back. Hi. Yeah.
Sir, it is a singular matrix. So the inverse of that.
Okay, we're getting a singular matrix.
Yes, sir.
Good. Because the idea is when I subtract 1, 2, 3 from here, right? So this is my 1, 2, 3. So if I subtract column 2 minus column 1 and column 3 minus column 1, so the matrix I get is 1, 2, 3. When I subtract 1, 2, 3 from here, I get 3, 3, 3. And when I get subtract 1, 2, 3 from here, I'll get 6, 6, 6. Okay. So that's good. You guys figured it out that the determinant is 0. But this is something I don't know if you did it as the first step or as the last step after finding the cofactor matrix. But if you guys would have been attentive to how I made the matrix, then it could have been clear to you that you see these vectors are not independent; they are dependent vectors. Okay, so because they are dependent vectors, it will come out to be as okay. So now this row and this row are ratios of each other. So row 1 and row 2 are in the ratio 1:2. So that's why obviously the determinant is going to be 0. Okay, fine. So then there's another problem here. So now A inverse, where do I use A inverse? So suppose I'm solving the system of equations Ax equals to B, and suppose it has a unique solution. Then the solution X will always be equal to A inverse times B. Because if I multiply by A inverse on both sides, then this thing becomes A inverse times A, which is identity matrix. So identity times X is equals to A inverse B, which means X should be equal to A inverse B. So when you have this case of unique solution, this unique solution can be found easily using A inverse. Okay. So that's there. So that's a property where you can use A inverses, where A inverse becomes important. All right. System of linear equations with n variables and n equations has a unique solution if and only if its matrix is non-degenerate. Non-degenerate means determinant A non-zero, and degenerate means determinant is 0. Okay, so degenerate matrix means determinant A is 0, and non-degenerate here is determinant A not 0. So this is a terminology which I am especially highlighting. This is something I've added later on because some textbooks, some exams, they just use the terms non-degenerate and degenerate instead of singular and non-singular. Okay. So a singular matrix is a degenerate matrix, a non-singular matrix is a non-degenerate matrix. So they are one and the same thing. The only thing is that if you don't know the definition, you get stuck in the exam. All right. Now, final thing is this particular determinant, finding this particular determinant. So you can employ the technique which I was talking about. So in this, what's happening is that the middle column is x1 to xn, n is odd. Okay, so it's basically an identity matrix 1, 1, 1, 1, and so on, everything 1. It's just that the middle column, instead of 1 and zeros, it has some values x1, x2, x3, and so on till x. Okay, so the aim is to find what's going to be the determinant of this particular thing. So you can use any method. Obviously, multiplication won't work here. At least I don't think it would be easy to do it using brute force. So you'll have to use some properties. Now, don't give up very soon. It's not like you तुमने एक तरीका try किया नहीं हुआ and then like so. Try 4, 5 things. Try, give it half an hour. It might take you time. ऐसा होता है कि in questions like this, there are 10 things which come to your mind. One of them will work, 9 of them will not work. Now it all depends on which ones you try first. If you are unlucky, you will try those 9 techniques which do not give the correct answer first, and the 10th technique will give you. But that's experience. That's how you learn कि कौन सी situation में कौन सी technique use करनी चाहिए. So my recommendation would be patient, try different things, whatever you have done. At the end of the day, I've told you one inductive method also to do such questions. So you can start with n equals to 1, then n equals to 3, then n equals to 5, n equals to 7, and so on, and then proceed. And that will give you some hint into what should be the general result for n cross n matrix, where n is odd. All right, so that wraps up the second chapter for linear algebra.
So you're going to take like the problem set doubts.
Okay, fine. I'll take the problem set doubts. Good. Problem set 1.
Yes.
All right. Okay. Okay. Yes. Tell me.
So for this, like there are only 2 equations given, and like there are 4 variables. You have to find the
Yeah.
complete solution. So
Yeah.
I'm getting different answers from the ones that you have given me. I don't know, like if
Okay.
someone else can verify.
All right. So let's do this first one. X1 minus x2. Okay. 1 minus 1, 5 minus 13. One minus 1, 5 minus 13. And the next one is 1, 1 minus 1, 1 times, let me call it that wxyz is equals to 3 minus 3. So obviously Gaussian elimination. So row 1 goes to row 1 minus row 2. So what I'll get is 1 minus 1, 5 minus 13, 0, 2 minus 1 minus 5, that's going to be minus 6, and 1 minus minus 13 is going to be 14. Wxyz is equals to 3 and minus 3 minus 3, so that's minus 6. Okay. After this, you can divide this entire row by 2, right? So if you divide this entire row by 2, what you get is 1 minus 3, 7, and here minus 3 again. So now obviously you will have solutions here, so it's not going to be a no solution thing. These two are going to be your pivot entries. Okay, these are your pivot entries, and so pivot variables w and x, yz are going to be the dependent variables because the only pivots are this, these, and these. Okay, so these are the only 2 pivots that you have. So everything is will be in terms of these vectors. Now can I make this more simpler?
You can add column, sorry, row 1 and row 2. For R1 is equal to R1 plus R2. So that the second entry in row 2 becomes 0.
Okay, so you can do it this one 0, right? So row 1 goes to row 1 plus row 2. So what I'll be left with is 1 minus 1, 5 minus 13. No, row, okay. Row 2 remains as it is, 0, 1 minus 3, 7. Now minus 1 plus 1 becomes 0. And minus 3 plus 5 becomes 2. And 7 plus minus 13 becomes minus 6 times w, x, y, z is equals to 0 minus. Okay. So then one of the equation becomes w plus 2y minus 6z is equals to 0. So w becomes equal to 6z minus 2y. And the second equation becomes x minus 3y plus 7z is equals to minus 3. Right? So x is equals to 3y minus 7z minus 3. Okay. So one of the solution becomes wxyz becomes just wxyz. Okay, suppose we have to first find the null space, right? We have to first find the null space. So we are going to solve this ax equals to 0, 0. Okay, let's find particular solution first. So x particular is equals to w, x, y, z, where I can take any values for y and z. So I'll take zeros. So w becomes 0, x becomes minus 3, y and z are any value. So this is my particular solution. Okay. And finally, null vector to solve xn, I will continue with this equation, which I have here. But the right hand side, I'll make 0, 0. At the right hand side, I'll make 0, 0. So to find xn, what I'll do is I'll work with this equation equals to 0. So I'm finding the null space vectors now. So equal to 0, 0. Ax equals to 0. So when I do that, I'll get the null space vectors. So here the first equation becomes this very same equation, because here also the same thing was same. So the first equation becomes w equals to 6z minus 2y. And the second equation, instead of minus 3 here, I would have 0. So the second equation becomes x equals to 3y minus 7. So now w, x, y, z becomes equals to 6z minus 2y, 3y minus 7z, y, z. So that becomes y times of 0, 3, 1, 0 plus z times of minus 2, 3, 1, 0 plus z times of 6, 3, 1, 0. Right. Are you getting a similar answer? Are you getting this answer? It changes. The problem is that it changes depending on what you did. Suppose I divided this entire row by half. If you don't do that, your answers might change. Like how they appear might change. So that's why finding the absolute answer here is pretty tricky.
Yes, sir, but I followed the same method like you did. So I guess it's
Okay. So x1 equals to, so w is my x1. So x1 equals to, basically what I have is x1 equals to 6. 6 times x3 minus 6. Yeah, 6 times x4 minus twice x3. So that's basically what I have. And 3x3 minus 7x4. Okay, so that's basically this thing. Minus 3. So this is the mistake I did. So this should be actually minus 3, right? This should be minus 3. This is my mistake. Maybe when I did solve it, I did not subdivide this part by 2. I should have done it. If I divide this row by 2, I should also divide this row by 2. That's what I didn't do back then. So yeah, so this should be minus 3. Rest of it is correct. Okay. Yeah. Some other question?
no, sir, I guess like the method that I followed is the same, so the answer should be right only.
Yeah.
This is
I mean,
this will be the method for all the questions, right?
Yeah. I mean, that would be the method
Yeah.
for all of them.
Yeah, and if in some question, like in that question we got 0 in place of x, but in some cases we will have x, right? For example, here it's 102 minus 6, right? So at some places we might have 1 or some other way, constant. So over there we have to substitute the value that we got.
In place. Acha, okay. Yeah. So here I got 0. So instead of 0, if I have, let's say, 7 or something.
No, not
So,
there, sir. Like in the second column, first or second column.
yeah. Here.
Yeah. First row, sir. First row.
First row, second column. So instead of this 0. So that's what I had here, right? I had minus 1 then. And then I did a second row operation to make this 0. So I can make this 0. So this is part of the Gaussian elimination. This is reduced Gaussian. So in Gaussian, you go in this direction. In reduced Gaussian, you go again back up, making things above the diagonal 0. So in Gaussian, what you go do is you make things below the diagonal 0 first, and then you go in a reverse direction, making things above the diagonal 0. So that is the reduced echelon form. So yeah, I mean, you can leave it here. You can use this technique to solve it, but it will be generally much more complicated looking. It is better to do reduced Gaussian, because then if there are more zeros, it's going to be nicer to look at. It's going to be nicer. The reason why I want this 0 here is because if I don't, if let's say I work with this equation, so what I get is the first equation becomes w minus x plus 5y minus 13z equals to. Now after this, the second equation is the same which I have here. So I have to substitute this equation now here to get w only in terms of the free variables.
Yes,
So
sir,
I
that's
cannot
what I
use
was
this
asking.
directly.
Yeah.
Yeah, so it's necessary here to make this 0 actually. You don't leave it like this, because if you leave it like this, then you will have an additional step which you will require to do now, which is substitute this x variable here and then solve for w as a function of y and z. Because ultimately what you want is every dependent variable must be in terms of just the free variable. Okay, every pivot variable must be in terms of free variables. So do Gaussian and reduce Gaussian. Do both of them. Make everything 0 as much as you can. As many numbers, coefficients becoming 0. And after that, you start making the equations.
Sir, is it possible that we get different complete solutions for some sums?
They would be different looking, but they won't be different. They would look different. They might seem different. Like if I had not divided this thing by 2 here. Okay, I divided these two rows by 2. If I would not have done it, my solution would look different, but it would not be different. Okay, the idea is that even if I do a simple column exchange here, what is a pivot variable and what is a free variable itself will change. So it's very difficult to compare answers here. The important thing is that the steps need to be correct, because the examiner, if he asks this in a subjective exam only, then he is going to look at what steps you are doing. So your steps have to be correct. So the final answer will not matter. What will matter is what steps you are following. So why don't you guys do one thing? Why don't you guys write down the steps and submit as an assignment to me? And I'll go through the steps. Let's say the first 5 till C part. Okay, just 5 of them. Okay, we have already done part A, so do from second one. So the first 5, B, C, D, E, F. So do these ones. Okay, B, C, D, E, and F. So you write down the steps and you submit, and then I'll go through them and I'll let you know if there are any others. Like take image, convert it into PDF, and then share it. All right. Determinants. So obviously, in this case, you had to use the properties to find these bigger determinants. Like going at it directly would be very complicated. So it would be advisable to use some property here instead of going at it directly. Have you done these problems, determinant problems?
No, sir, I haven't.
Okay, fine. Now that we have discussed determinants in much more detail, why don't you guys have a second go at it? Try to use properties. Okay, so let's say I do one of them as example. So let's say this option number D looks slightly complicated. So let me copy this one. So let's say I want to find the determinant of this one. So obviously this column is slightly easier to maneuver. I can take a 4 out of this column. So I can write this as 4 times determinant of yeah. Can I make any other columns easier to maneuver? Okay, let me write this as 1 0 0 minus 1 0 and 1 1. Okay, I'm doing an exchange. So the next column. So I'm doing this exchange. So I'll put a minus sign in front of it. 4 minus 4 minus 4 1 minus 4. (11) minus 2 minus 2 5 minus 11. 9 6 minus 9 minus 6 minus 2 7 5, and first row now comes to the end. 1 minus 1 minus 9 minus 8 and 7. Okay, next what I can do is 1
transpose,
times.
right? You can take a transpose also.
Yeah, I can do transpose, but I don't have any problem working with columns. You can do it if you have an issue working with columns. I'm trying to look at how to simplify the things inside furthermore. So this becomes basically 1 times determinant of this thing, 4 minus 4 minus 4, 1, 11 minus 2 minus 2, 5, minus 9 minus 6, 6, minus 2, 7, and 1 minus 1 minus 9 minus 8. And this would be plus minus plus minus. So again, plus 1 times determinant of, if I remove this column in this row, so 4 minus 4 minus 4 minus 4, 11 minus 2 minus 2 minus 11, minus 9, 6, 7, 5, 1 minus 1 minus 9, 7.
So not 7 minus 2. Minus 9, 6, minus 2, and 5. The third column. It will be minus 9, 6, minus 2.
I'm removing this row. The fourth column would be 1 minus 1 minus 9, 7, right?
Third column, sir. Third.
Okay, third column, 9, 6,
Minus
minus 2 and 5. Yeah. Thanks. Okay, so what can I take common now? Take anything common here. 11 minus 2 minus 2, 5. 2 minus 2 minus 2 minus 9. Here I can take 4 common and do Gaussian elimination. Here also you can do this Gaussian elimination. You can exchange the rows. 4, 11 minus 9 and 1. And okay, so you can exchange the rows. The two rows will exchange each other. So which was the row which I had? First row I had eliminated. So this becomes minus 4, minus 11, 5, and 7. And this was, so I had eliminated, which row did I eliminate? The first thing I had to do was eliminate these two rows, right? So this one. Okay, I eliminated a wrong row.
Yeah, sir, you eliminated. I was wondering that.
Yeah, I eliminated a wrong row.
You eliminated the last row.
Anyway, so I want to keep this first now. I want to make this thing first. So I'll put this first and I'll put this last. So the first row becomes 1, 5, 7, minus 8. The second row remains as it is, minus 4, minus 2, minus 2, minus 9. The first row comes in place of the third row, minus 4, minus 2, 6, minus 1, and minus 4, minus 11, 5, and 7. All right. So I did a row exchange, so there's a negative in front of here. And then I can do column operations, row 2 minus row 2 plus 4 times of row 1, row 3 plus 4 times of row 1, row 4 plus 4 times of row 1. So these three things will become 0, and then you will be left with a simple 3 cross 3 matrix times 1. as your final answer. Okay, you'll have to do these row operations, and here you can take 4 common out, so all these become 1, and here you can do the row operations. Row 2 goes to row 2 plus row 1, row 3 goes to row 3 plus row 1, row 4 goes to row 4 plus row 1. Okay, and then again these 3 entries become 0, and then you are left with a simple 3 cross 3 matrix. Okay, you'll still have to do some calculations, but the idea is to make it as less as possible. Okay, so do some tricks to reduce your calculations, reduce the burden of calculation. All right, so you can use some similar techniques in the remaining problems. Obviously, problem number A, a lot of things seem to be coming out common. Other problems, not so much. So some questions might need you to work much more harder than others. But try to think in terms of shortcuts rather than brute force, because brute force anybody can use, right? But it will be very time consuming in an exam. Finding a 5 cross 5 determinant in an exam would imply first you have to find 5 4 cross 4 determinants. For each 4 cross 4 determinant, you have to find 3 cross 3 determinants. So that becomes very complicated in exams. You can't do that, obviously. You wouldn't have the time or the number of pages to do such difficult calculations. So it's always better to think in terms of how to reduce your calculations. All right. So I don't think I have time to start the new topic now. Have you guys done past years of linear algebra?
Not yet, sir, but LADW also you asked us to solve.
Oh yes, LADW. Yeah. Which questions? Page number 11. Right. Okay, find a basis in the space of 3 cross 2 matrices M3 cross 2. So in the space of 3 cross 2 matrices, I have to find a basis. 3 cross 2 matrices are matrices with the 3 rows and 2 columns. So A1, 1, A1, 2, A2, 1, A2, 2, A3, 1, A3, 2. So these are matrices M3, 2. So I have to find a basis in this space. So first of all, how many vectors will the basis have? How many matrices basically should be there in it? How many?
3.
3. Okay. Any other answer? Okay, the answer here is 6, because each of these numbers is a separate entity in itself. So your basis will be of the format this vector, and so on. So you get the idea. एक एक करके सबको 1 1 करो. So that would be one of the bases. Okay, so now you can think a 3 cross 2 vector as a simple vector in 6-dimension space. A11, A12, A13, A21, A22, A23. Every 6-dimensional vector can be broken down into a 3 cross 2 matrix. पहले 3 एलिमेंट्स को फर्स्ट कॉलम, बाद के 3 एलिमेंट्स को सेकंड कॉलम. So a 3 cross 2 matrix is nothing but a R6 element, R6 vector. So since it has 6 different entities, each of which can be any real number, the basis vectors are going to be 6 vectors in the basis. And one of these basis vectors is this one. Now, if you convert these 6 vectors in the R6 space, the first is going to be this The second is going to be, and so on. So these will be your 6 different vectors, which are basically the basis vector in our sets. Okay. So the number of basis vectors is determined by how many entities you have to decide for. So that will give you the number of basis vectors. And the number, once you figure out कितने चाहिए, उसके बाद you can easily write them down. एक एक करके सबको 1 करो rotation में, keeping everything else 0. So that's how you get it. Okay, true or false? Any set containing a 0 vector is linearly dependent. True or false? Come on, I need answers. I don't want you guys to be solving it right now.
True.
Have you guys
Sorry.
attempted it? It doesn't seem like you have attempted it. It seems like you are solving it right now. If you guys need more time, discuss it next time. But the point is, you should be thinking about it first. And see, I know exam is not right off the corner. Last week DSC का exam हुआ है, so you feel like कि अभी तो एक साल पढ़ा है. It becomes very difficult to focus given these circumstances. But try to find some time. Be a little more regular. That's all it takes. Important topics we are doing here. Basis is pretty important, I feel. So you take your time, you do them, and we can discuss them next time. But do it. Okay. I mean, it's good that you remember कि ये दिया था. But I'll be much more happy if you also come prepared for it. So why don't I just add this as an assignment as well, for which you have to give me the answer. So I'll add this and the 5 questions from problem set as an assignment. I'll join them up. I'll upload it, and then you guys are supposed to submit your answers. Okay.
Sir, I had one doubt with respect to basis. Can there be multiple bases?
Yeah, sure. Why not? ये रहा दूसरा basis.
But like,
ये लो बन गया दूसरा
the
basis.
definition of basis is it's unique, right?
No.
For vector space.
No, a basis is not unique. Any vector can be represented using the basis in a unique manner. So suppose this is my basis, and a vector in M32 is going to be, let's say, 1, 2, 3, 4, 5, 6. And let's say I call this vector as V1, V2, V3, V4, or rather M1, M2, whatever you want to call them, V5 and V6. So this matrix is going to be 1 times V1 plus 2 times V2 plus 3 times V3 plus 4 times V4 plus 5 times V5 plus 6 times V6. There is no other way to represent this in terms of the basis vectors. The other thing is spanning system. So suppose in this very system of vectors, I add one more vector, which is W, which is, let's say, 0, 2, 0, 0, 0, 0. So it is just twice of V1. But now the set V1 through V6 plus W is a spanning system and not a basis. So if I want to represent the same matrix now, I can represent it as 1 times V1 plus 1 times W plus 3 times V3 plus 4 times V4 plus 5 times V5 plus 6 times V6. Okay. So now if I use these 7 vectors as a combo, I have multiple ways. This is also correct and this is also correct. So now I have multiple ways of representing the same matrix. So that's what I say. That's what I mean when I say that when you have basis, when you have a basis, every vector like this one can be represented in a unique way. But when you have a spanning system, which is not a basis, then you have multiple ways to represent some vector.
Yes, sir. Got it. Also, sir, one doubt is a little silly. I just wanted to confirm that the column vectors in a matrix also belong to the column space of A, right? Like, obviously, they
Yeah,
would be.
obviously,
Okay.
obviously.
Yeah.
Because you take 1 times that column and 0 times other column, you get the first column itself.
Yes. Sir. Okay.
So it belongs to the column.